The next field is fragmentation offset. Fragmentation offset in unit of 8 octets or 64 bits. This specifies a value for each data fragment in the reassembly process. Different sized MTUs, which stands for maximum transmission units, can be used throughout the internet. So here we have IP datagram. In this IP datagram, we would have header here, and here we would have data. So it would be header plus data. The data can also be referred to as payload. So this IP datagram is a part of frame which is created at data link layer. So here we must have the MTU, the maximum length of data to be encapsulated in a frame. So this size must be specified. The value of MTU differs from one physical network protocol to another. For example, the value of a LAN is normally 1500 bytes, 1500 bytes. But for WAN, it can be larger or smaller, depends. So here we have different MTUs for some networks. For hyperchannel, we have around 65,000 MTU. For tokening, we have around 18,000. It is actually 17,914. For token ring, we have 4,464 and so on. So these are the MTUs for some sample network protocols. Let's consider an example. This figure shows a datagram with the size of 4,000 bytes. This one is the IP datagram having 4,000 bytes. And this IP datagram is fragmented into 3 frames. The bytes in the original datagram are numbered 0 to 3,999. The first fragment carries byte 0 to 1,399. The offset for this datagram is 0 by 8, which equals to 0. The second fragment carries bytes from 1400 to 2799. The offset value for this datagram is 1400 divided by 8, which is equal to 175. Similarly, the third fragment is starting with 2800 and ending on 3999, and the offset value for this fragment is 2800 divided by 8, which is equal to 350. Remember that the value of offset is measured in units of 8 bytes. This is done because the length of the offset field is only 13 bits long and cannot represent a sequence of bytes greater than 8191. This forces hosts and routers that fragment datagrams to choose the size of each fragment so that the first byte number is divisible by 8. This figure shows an expanded view of the fragments in the previous figure. The original packet starts at the client and the fragments are reassembled at the server. The value of the identical field is the same in the fragments. The value of the identification field, this one, it is same in all the fragments as the value of flags here, with more bit set for all fragments except the last one. Here we have 1, here we have 1, and this one is 0. So it means that more fragments, and last fragment. Also, the value of the offset field, this one, and this one, these are shown. We calculated these three offsets in the previous slide. Note that although the fragments arrived out of order to the destination, they can be correctly reassembled due to these values. Now we are going to have some examples for these three fields. We will have some values for these fields and will calculate some outcomes, or here in the fragment these values. So first example about the second word in the IP datagram or the IP header. A packet has arrived with an M bit value of 0. Is it the first fragment, the last fragment, or a middle fragment? Do we know if the packet was fragmented? So the M bit value is 0, means this one bit is 0, more bits. So this can be 1 or 0. If it is 1, then it would indicate that there are some other fragments. And if it is 0, then it would indicate that this fragment is the last one, or this is the only one fragment. So if the M bit is 0, it means that there are no more fragments. The fragment is the last one. However, we cannot say if the original packet was fragmented or not, because a non-fragmented packet is considered the last fragment. So in case we have 0 here, then we have two options. The first one is this is the last fragment, and there is another possibility, that is this is the last packet and also this is the only packet. So for M bit we have these possibilities having 0. Then next example, a packet has arrived with an M bit value of 1. Is this the first fragment, the last fragment, or a middle fragment? Do we know if the packet was fragmented? Now, if we look into IP datagram here or here, M bit is 1 in this case. So, what it would be, first fragment, last fragment, or middle fragment, and whether there is fragmentation or not. So, if M bit is 1, it means that there is at least one more fragment. If it is 1, then it would mean that there are some more fragments to come. This is not the last fragment. So this is obvious that we have more than one fragments. This fragment can be the first one or a middle one, but not the last one. For last one, we must have 0 for this M. We don't know if it is the first one or middle one. We need more information. The value of the fragmentation offset. We need this value. Then we have another example. A packet has arrived with an M bit value of 1 and a fragmentation offset value of 0. Is this the first fragment or last fragment or middle one? M is 1. It is either the first fragment or a middle one. Because the offset value is 0, therefore it is the first fragment. Here, if you look into this fragment, M is 1 and this offset is also 0, so it indicates that this fragment is the first fragment. So if we don't have this value and we have only one, then this would be either the first fragment or middle one, but not the last one. Then we have another example. A packet is arrived in which the offset value is 100. This value is 100. What is the number of the first byte? Do we know the number of the last byte? To find the number of the first byte, we multiply the offset value by 8. This means that the first byte number is 800. But we cannot determine the number of the last byte unless we know the length. We don't have length in this question, so we cannot determine the number of the last byte. Next, a packet is arrived in which the offset value is 100. The value of header length is 5 and the value of total length field is 100. This one is 5 and this one is 100. What are the numbers of the first byte and the last byte? So the first byte number is 100 by 8, so it would be 800. The total length is 100 bytes and the header length, as we know, is 20 bytes, which means that there are 80 bytes in the datagram. So if the first byte number is 800, then the next would start from 880, and in this datagram the last number would be 879. Next is time to live. It tells a network router whether or not the packet has been in the network too long or should be discarded. Time to live, or TTL, refers to the amount of time or hops that a packet is set to exist inside a network before being discarded by the router. Each packet in the network is set with a life. So that life, in case expires, then that packet would be discarded or dropped by the router. Every time a router receives a packet, it subtracts 1 from the TTL count and then passes it on to the next location in the network. Suppose the TTL value is 10 and it is received by the router. So the router would pass that packet towards its destination, but before passing that packet, it would reduce its TTL by 1. So if it is 10, after that it would become 9. If at any point the TTL count is equal to 0 after the subtraction, the router will discard the packet and send an ICMP message back to the originating host. So if TTL becomes 0 after the subtraction, then that packet would be considered as expired and that would not be forwarded by the router. We have an example. An IP version 4 packet has arrived with the first few hexadecimal digits as shown. Here we have some hexadecimal digits for this IP version 4 packet. How many hops can this packet travel before being dropped? The data belong to what upper layer protocol? To find the time to live field, we skip 8 bytes. 4 bytes plus 4 bytes, 8 bytes. So this one is the ninth byte. So we are skipping 8 bytes. The time to live field is the ninth byte, which is 01. This one is 01. A hexadecimal digit takes 4 bits. So two hexadecimal digits. So two hexadecimal digits are equal to 1 byte. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So till here we have 16 digits, means 8 bytes. So from here the ninth byte starts. So this one is 09 for ninth byte. For 10th byte we have 02. 10th byte is taken by the protocol. This means the packet can travel only one hop. The protocol field in the next byte 02, which means that the upper layer protocol is IGMP. This one is 02. Here we have protocol in the next byte. So this one indicates that it is IGMP. This one values for code points. Here we have IGMP, which is 2. The next field is protocol of 8 bits. The 8-bit protocol field indicates the protocol that will receive the data payload. For example, ICMP, the Internet Control Messaging Protocol, has a protocol number of 1. TCP, Transmission Control Protocol, has a protocol number of 6. UDP, User Datagram Protocol, has a protocol number of 17. Similarly, RPD, Reliable Data Protocol, has a protocol number of 27, and so on. So we have different protocols, and these protocols have some numbers through which these protocols are identified. Here we can have ICMP, IGMP, SCTP, TCP, UDP, DTCP, OSPF, and there are so many other protocols. The value of the protocol field defines to which protocol the data belongs. Here, if we have a number, so that number would identify that this data would go to that particular protocol, or we can say that that protocol can process or understands this data. We have some sample protocols here, and we have some values for these protocols. Next field is header checksum. It is similar to the checksum which we studied in the TCP and UDP datagrams. It is also taking 16 bits as we saw it in our previous lecture of TCP and UDP. So error checksum is used for the control of error, and this is used for header only. It is just like transport layer which we studied. We have an example for calculating the checksum. So here we have the header, and we have some values in this header. So here if you look into this header, we have 32 words, 32-bit words. Like here we have 32 bits, then 32 bits, 32, 32, 32. But in fact, for checksum, we need 16 bits. So we are going to take 16 bits from here, 4, 5, and 0, convert it into hexadecimal, then 28, convert it into hexadecimal, then here 16 bits, 1, this one is converted. Similarly, all these values are converted. The IP addresses are also splitted into two parts. 1012 is taken, then 14.5 is taken. So then sum is calculated of all these hex, and one's complement is taken of this sum. So this one is the checksum for our header. It is just like transport layer. In the last lecture we did this thing, but that time we converted the fields into binary bits. There were blocks of 16 bits. Then we have source IP address and destination IP address. IP address of sending and receiving hosts in the network. We have already studied about the IP addresses, and each IP address takes 4 bytes if it is of version 4. So here we will have 4 bytes for source IP address to identify the source host, and here we will have the IP address of the destination host that would also take 4 bytes. The last thing is option. IP options is used for testing, debugging, and security. Padding bits can also be used to adjust the size of the blocks. So here the size of block is 32 bit. If the option is taking, let's say for example 30 bits, then we must add 2 additional bits, and those 2 bits would be considered as padding bits. The options can be single byte or multiple bytes, but the size of each word must be 32 bits. So here we might have single byte or multiple bytes. First one is no operation under single byte, means a no operation option is a 1 byte option used as a filler between options. An end of option is 1 byte option used for padding at the end of the option field. It, however, can only be used as the last option. Then we have multiple bytes. The first one is root record root. This option is used to record the internet routes or the internet routers that handle the datagram. It can list up the 9 router addresses. It can be used for debugging and management purposes. Then we have strict source route. It is used by the source to predetermine a route for the datagram as it travels through the internet. Then we have loose source route. This option is similar to the strict source route, but it is less rigid. The router in the list must be visited, but the datagram can visit other routers as well. The last thing, timestamp. Timestamp is used to record the time of datagram processing by the router, and this one is measured in milliseconds. Also, the universal time or Greenwich Mean Time is considered. This was all about IP datagram. In this lecture, we studied all the fields in IP datagram header. I hope you will also explore this topic by yourself. If you have any comment, put your comment in the KCMS. Inshallah, I will respond you. Thank you.